Okay, so welcome back to the propulsion class. Hopefully I've had a good weekend. I guess at this point, I'm already exhausted with this semester, so I'm ready for it to be done.
Just make it online.
Huh?
Just make it online.
That's actually that's gonna be worse. I think. just be done. I'm ready to give you all an A and just be done with it. But so the last thing we talked about was, I think, this page, right? We didn't finish the compressor, did we? Okay. So your homework is posted before starting the lecture. Your homework is posted, and I saw that most of you guys who are in the class have already submitted your quiz. But I think there are a couple of students who don't watch the online lectures and don't take the quizzes or submit any homework. So
Really?
yeah, so this is, since we are recording this, I'm just telling them if they end up watching the lecture, please submit your work. Otherwise, you will fail the class. So yeah, thank you. If you could please close the door. And okay.
The quiz this will be similar to the homework problems.
This week's quiz is actually going to be two problems, because one of them will be just explanation of something, so very small, short, and the other one will be pretty short. So it will be pretty similar to your homework problem number 2 through 5. So number 1 is actually the hardest question of the homework, but 2 through 5 are pretty easy and straightforward. You just plug and chuck. So this week's quiz will be 2 problems, but it shouldn't take you more than definitely not more than an hour to solve the problem. So let's go back to the discussion. I think it is. So I was thinking to finish chapter 4 this week, as you recall, but I don't think we're going to do it because there are a lot of material that we haven't covered yet, and I don't want to just run over, man. I don't want to go over them fast. I want to focus on all of the topics and discussions for you guys to have a complete understanding of the material. Okay? So during the last lecture, at the end of the last lecture, this was the last slide we covered. Essentially, we found an equation for the compressor efficiency, which was related. It was a function of compressor pressure ratio and compressor temperature ratio, right? Using this equation, if you recall. And we already know that your compressor temperature ratio is related to compressor pressure ratio through a relationship that looks similar to isentropic relationships. The only difference is the presence of your small stage efficiency. You just have to keep in mind that your small stage efficiency is doesn't really change. We can assume it's constant for a compressor, so it can be it can be assumed constant throughout the process of a jet engine operation. And here on the left-hand side of the slide, you can see, on the right-hand side, the right-hand side of the slide, you can see the compressor pressure ratio versus the compressor adiabatic efficiency. So essentially this relationship, right, for different small stage efficiencies. Hopefully you guys remember the small stage efficiency and the difference it had with the regular compressor efficiency, right? So you had to take the derivative. Just to refresh your mind, we defined the small stage efficiency as this: the derivative of the changes in isentropic enthalpy versus the derivative of changes, the small changes, the small enthalpy change versus the non-isentropic, the real enthalpy. But for the regular efficiency, we just compare the exit and the inlet of the compressor. Okay. So moving on, that's essentially the last thing we want to talk about in our discussion on the compressors is the stagnation versus static condition. So as we all know, the difference between the stagnation and static condition is your kinetic energy, essentially E squared over 2, right? And for your compressor stage, compressor goes from station 2 to station 3. The total, your main focus is going to be, should be on the changes in the total conditions in general, not the stagnation. Was be essentially one of your goals or one of your desires in designing a compressor is to keep the velocity the same at the inlet and the exit. So the changes in kinetic energy, you want to minimize the changes in kinetic energy. And as for reasons why we want to keep the changes in kinetic energy to a minimum value or to 0 essentially, we will talk about it a little more in one of the later chapters, chapter 8, I think, when we talked about the actual compressors. So essentially, the difference between the velocities at the inlet and the outlet has to be negligible. Is desired to be negligible. Is there any questions about the compressor analysis? No. Okay, just a summary of the compressor analysis we have seen. A real compressor flow may be considered adiabatic, which means that Q of compressor is essentially 0. The energy transfer to the fluid due to the shaft in a compressor is several orders of magnitude higher than any heat transfer that takes place through the casing. Thus, heat transfer is neglected. Viscous dissipation in the wall body layer and shocks account for the source of irreversibility in a compressor. We have two main figures of merit, if you will, that describe the compressor efficiency. One is the adiabatic compressor efficiency, eta of C, and the other one is the polytropic or a small stage efficiency, E of C. And the two compressor efficiencies are actually related to each other. The compressor polytropic efficiency is independent of compressor pressure ratio, whereas the compressor adiabatic efficiency is a function of the pressure ratio and decreases with increasing pressure ratio. And to achieve a high pressure ratio in a compressor, multi-stage and multi-spool configurations are needed. Now we have talked about, did we talk about the multi-stage and multi-spool configurations? Just a little bit, just an introduction to it, right? Okay. So, we already know that. So let's solve an example for the compressor analysis. This is a book example, as the previous examples we have solved. It says a multi-stage axial flow compressor has a mass flow rate of 50 kilograms per second and a total pressure ratio of 35. So your m dot is 50 kilograms per second. That's m dot and not dot, and the total pressure ratio pi of C is 35, right? The compressor polytropic efficiency is 0.9, E of C is 0.9. And the inlet flow condition to the compressor is described by the total temperature, that's T2, TT2, 288 Kelvin, and PT2, 100 kilopascals. Assuming the flow in the compressor is adiabatic, and the constant gas properties, and assuming the constant gas properties through the compressor, meaning that gamma is 1.4 and we have a constant Cp of 1004, we want to calculate the compressor exit total temperature in kelvins. Okay. So how should we go about solving this problem? Using the equations we already have had, how can we answer part A of this problem? what do we have? We have the pressure ratio, right? We have gamma, and we have the small stage efficiency or the polytropic efficiency, right? Did we have any relationship that related the temperatures to pressures and using the polytropic efficiency? Do we have the adiabatic efficiency? You can definitely use the definition of adiabatic efficiency if you have the isentropic conditions as well, right? But we only have the small stage efficiency, E, right? So go back to the relationships you have. Let me actually go back here as well. If you can see, the compressor total temperature ratio could be related to the pressure ratio through a relationship that was similar to our isentropic relationship, right? So gamma minus 1 over gamma. The only difference was this small stage efficiency. That's actually what we used in the adiabatic efficiency calculations in the next slide as well, right? That's what we replaced temperature ratio with, right? So do we have the compressor pressure ratio, right? We have gamma and we have E of C, okay? Which essentially means that you can calculate the temperature ratio. What would be the temperature ratio here? So when solving these examples, I expect you guys to, all of you guys, to solve this, okay? Do the calculations, do the solutions, right? And essentially, if I see not all of you are contributing to the solution, I will make it a quiz. Just a 10-minute, 5-minute quiz. So
we're using the tau c from pi c equation?
Tau c is equal to pi c to the power of gamma minus 1 over gamma multiplied by E of c. Right?
And then pi c is just the pressure ratio, right?
That's the pressure ratio. So whenever you see pi, that's actually something that is not explained in the book for whatever reason. But whenever you see pi, we are talking about pressure ratio. Whenever you see tau, we are talking about the temperature ratio. Yeah, that's the hard part in the cycle analysis. Other than that, you all have all the equations, right? When you're analyzing a cycle, you have to make sure that you are getting the ratios correct.
I like it better like in orbital mechanics when you do everything on the board, but now you can't. Because then we know which equations are important in this.
Yeah, that's we can actually we can we can talk about that. Let's do this. Okay, so this is essentially a plug and chug, right? You have pi of c is 35 to the power gamma minus 1 is 0.4 over 1.4 multiplied by 0.9, right? Let me actually make sure that I write the equation here. So this is the equation we are using. So anyone? Is there anyone who got the answer? 8? Okay. The solution, so did use the same equation that I had here, so 35. You got 890.
When you multiply that by TT2, right? No?
You're talking about the final temperature then? Okay, no. What did you get for the temperature ratio?
3.09.
Okay, yeah, that's correct. And what did you get for the final temperature?
890.
890. Let me see if this is correct. Yes, 890.4. So what about the next part? 0.4 Kelvin. How should we find the adiabatic efficiency? You have, if you recall, we had this equation that related adiabatic efficiency to your pressure ratio, right? Go ahead. That's it, right? Tau of C minus 1. Right? That's it. So you just plug those in, and what will we get if you plug these in? Exactly, 0.84. So for 84% essentially. So your adiabatic efficiency is going to be 80% compared to your small stage efficiency, which is smaller. Okay. And the last part is the compressor shaft power in megawatts. Okay. You have to get a little creative here because we didn't have, I don't think we had a direct equation for this. How can we calculate the shaft power here? Just think about it. Don't go back to your equations. Just think about it. How can we calculate the shaft power in a compressor? What is the total? So essentially, the shaft power in the compressor should be equal to the total power output of a compressor, right? In an ideal condition, right? So, what is that? What is your total power output of your compressor?
Total pressure ratio.
So essentially, what is the parameter we use that represents the total energy of the system? Total enthalpy, right? Total enthalpy, exactly. So the total enthalpy, essentially total energy of your system is going to be total enthalpy at the end stage minus the total enthalpy at the beginning stage, initial and like final and initial stage. That's it, right? So essentially your total compressor exit must be m dot. Your total power must be m dot multiplied by total enthalpy change, right? And enthalpy is CPT, so m dot Cp total temperature, the difference in total temperature. Do we have the total temperatures? Yes. Do we have Cp? Yes. Do we have m dot? Yes. So we can calculate the total shaft power. Okay, let's do that. Let's calculate the total shaft power. So what I'm saying is that your compressor shaft power, which is P of C, is m dot HT3 minus HT2, which is equals to m dot Cp TT3 minus TT2. That's it, 30.2, right? 30.2 megawatts. Okay. Is there any questions for this problem?
So TT3, that was the tau C?
No. Tau is a temperature ratio. Tau of C is a compressor, is the compressor per temperature ratio, right? Which means that it is T3 over TT2.
Oh, you multiply 288 by 3.09 and get 890?
You multiply 309 by 288 to get the 890. Yeah. That's it, yeah. Okay, any other questions? So just keep in mind, most of the problems you're going to get, even the hardest ones you're going to get in the cycle analysis, is going to look like this. So essentially, there is no creative thinking. You just have to make sure that you are consistent, right? And the hardest part is so essentially, what happens is, I give you the zero station parameters, then I ask you to find the exit, the V9 and whatever parameters we have at the nozzle exit, essentially, right? So you have to go, it's going to take a long time, but it's not that hard, right? Hopefully it's not that hard, right? But in this, the current homework you have the question 1, essentially you have to do a multi-stage cycle analysis. You have to go step by step. But we are going to get the toughest questions in the next homework, which is going to be posted next week. Okay. Okay. So let's talk about the burner. Let's move on from compressor to the burner or the combustor, right? The burner, what you have here is a schematic of a burner. So we have after the compressor. What is going on here? Huh? It is coming from here. It's like there's a fan here. We have a pre-diffuser, but after the compressor, we have a pre-diffuser that is supposed to diffuse a little bit, diffuse your whatever going into the combustor a little bit. And we actually divide this thing, the whole thing, to two sections, right? One section is going to bypass the igniter, and it is going to be added to the ignited gas, the exploded gas, essentially, later on, to help with the burning all the remaining fuels and everything. And then it will move on. We will have all the process. We will have some intermediate holes that will take in the bypass air, if you will, the bypass compressor air, if you will. And eventually the exhaust gas will go out of the combustor and go to the turbine. Okay, but we are not really concerned, because we are doing a cycle analysis, which is systems level analysis. We are not really concerned with what's happening inside the combustor, the same as with compressor. We were not concerned with what is happening inside the compressor. We were just concerned with the inlet and the outlet. So the same thing is true for a combustor or a burner as well. So we are sorry. I think this is being recorded. So online people, sorry guys, you just hear just a lot of noise. But yeah, we are not really concerned with what is happening inside the combustor. We are only concerned with the inlet conditions and the outlet parts, right? So we have two inlets in the combustor compared to the one inlet and one exit for the compressor on all the other parts. So the only section that really has two inlets is the combustor, which we have M.dot fuel coming in. So we have the fuel injection and air coming in as well. So we can write a very simple mass balance, right? Whatever is coming in, it has to go out, right? That's going to be your mass balance. We can also have an energy balance, right? The total energy at the inlet for air is going to be m.0 HT3 or the fuel is going to be your QR of the fuel, which is the fuel heating value, multiplied by eta of the combustor, which we'll talk about, or burner, which we'll talk about later, multiplied by your end dot fuel, and whatever is going out is going to be the total enthalpy at the stage 4, which is the exit for the output of the combustor, multiplied by the total mass that is going out. Okay, but inside the combustor we have a lot of processes happening. So Dr. Wang is actually, and Dr. Farooq, both of them, are very interested in whatever is happening inside a combustor, for example. So the reactions, the atomization, vaporization, the mixings, and whatever that is happening inside a combustion chamber in general, right? But it's not the focus of this course, of course, because we are doing a cycle analysis. Okay. So, but in general, to put in a most general term possible, in a combustion chamber, in a combustor, or in a burner, in this way we call it burner. Wherever you see subscript B, is talking about the combustor or burner. But I'm very used to the word combustor, so don't get confused, right? Or ask questions if you will. So the fluid is being added, the fuel is being added to the air, and through it we have some igniter that are going to ignite, and we will have the combustion process happening. It's an exothermic process, which means that we will have a heat release. We will have huge heat release after the combustion. Okay. Okay. An ideal burner as an ideal burner's process is a reversible process. But then the question is, what is an ideal burner? How can we have an ideal burner? What does a reversible process mean? It means that there is no changes in entropy, right? And you just think about it. You have combustion happening, essentially explosion happening inside the combustor, right? And we are saying that it is possible to have an ideal burner with explosion inside. It is possible for its process to be reversible, right? How is that possible? What do you guys think? Yeah. What do you guys think? What is an ideal burner? How can we have? To put it in layman terms, how can we have? It's not going to be layman terms. But how can we have explosion without increasing entropy? Yeah, entropy is not layman term, right?
Isn't the whole point of having combustion to increase entropy?
Is it? Why would you don't want to increase entropy? Entropy increases side effect, right? You want to add momentum too. It depends on the process. But yeah. So what do you think? Let's start from Tyler. How can we have an ideal burning process, which is reversible?
Maybe like the forms of energy that are generated are like cleanly converted from one to the other. So like increasing the energy of the mass in the burner, like that is like 100% translated to kinetic energy at the exit.
But that doesn't talk about your reversibility of the process, right? It's just going to be, it just means that you don't have any sort of losses in the energy transfer, right? But so how would that happen? Let's say that's the case. How would that happen though? Let me change the question a little bit. What is the biggest irreversible part of combustion in your mind? Is I mean, we can have reversible chemical process in an ideal world, right? So a chemical reaction is not, you meant chemical reaction, right? Not chemical change.
Usually when you burn something, in a chemical reaction with burning it, it's usually not a reversible process.
So like the explosion part, right? The explosion part itself is that it seems very messy, right? It seems that that's the part that is responsible for the irreversibility, which means that it happens very suddenly, right? It happens in a snap, that's it. You're gonna have explosion or combustion, right? It's going to happen. So based on that, if we can essentially slow the process down a bit, we are going to decrease the irreversibility. We are going to decrease the entropy, the rate of change in entropy, right? Rate of entropy increase. Does it make sense?
So kind of like expansion waves, how they're very gradual, which is why you can still consider them isotropic.
Kind of. That's a good example. But what about shock? Are shock isotropic?
You have to know the syntax reaction, where you said you're trying to not only the combustion of the entire fuel and air at the beginning, but throughout the combustor. Does that have to do with the reversibility?
That's actually so you both are pointing to the right direction, right? But we are talking about the real ideal case, which never happens, right? And it's very hard to actually go through that direction, right?
So just like out of curiosity, if you look at it from like a mathematical point of view, if you look at like the SDT, you're just increasing VT essentially, so you're making like the whole thing really small.
You're increasing the changes in temperature.
Changes in time, like if you.
DSDT, okay. That T. Yeah. That's actually one way of looking at it. That's one way of looking at it, definitely. And based on, to go off of what you guys said, essentially in an ideal process, your flow is so slow that you can just say that Mach number is close to 0. That's the idea of an ideal burner, which is never the case for us, right? Or never the case anywhere. But so as long as we have the wall friction, the turbulent mixing, and the chemical reaction happening at a finite Mach number, right? Your process is not going to be reversible. But what would happen? Can we say, let's say your process, your burner is reversible. Can we say it is isentropic? No, why not?
Because there's still big addition of heat.
Exactly, it is not adiabatic. So that's very important, right? That's one of the few parts that you have this non-adiabatic process happening. Okay, so which means that for an ideal combustion chamber, your total pressure ratio, pi, is 1, right? But we don't have the ideal combustion chamber. We have a lot of losses, so we have a lot of total pressure loss, right? So your total pressure ratio, which is going to be P total pressure at the station 4, divided by total pressure at the station 3, is always smaller than 1. There is this guy, Kerbrock, who came up with this approximation, and named it Kerbrock approximation, to relate the pressure ratio to Mach number through a constant, by introducing a constant epsilon, which is the proportionality coefficient. Right? So if you had to use this equation to find the pressure ratio, I will give you the proportionality coefficient. So you just assume constant, but the proportionality coefficient is always between 1 and 2. And using this approximation, you essentially can find a combustor pressure coefficient using a combustor's Mach number. And this approximation is only valid for subsonic flows. It is definitely not valid for supersonic flows. Okay, so let's try to find the equation. Let's try to calculate the efficiency. Let's try to calculate the efficiency of a burner or a combustor. The first thing you want to do is to write the conservation equation. Conservation of mass is going to be your m.4, which is your exit. Mass flow rate is going to be just a summation of your inlet mass flow rate, which is m.0 plus m.f, and we have already defined the f as fuel to air ratio. So essentially we can take the m.0 out and rewrite the equation as m.0 multiplied by 1 plus f. Okay, we can write the energy balance. The input energy is going to be m.0 multiplied by ht3 plus m.qr multiplied by 8 of burner, which has to be equals to your energy at the outlet station, exit station, or station 4. It's going to be your m.4, which is m.0 plus m.f multiplied by ht4, and we can rewrite that as m.0 multiplied by 1 plus f ht4. Okay. But how do we, this is actually how we define the efficiency of the burner. The efficiency of the burner is going to be the actual heating value of the burner divided by the ideal heating value of the burner. Okay, so in your energy equation, you essentially just have to be mindful of the fact that here, in your energy conservation equation, here in this, I'm talking about the second term, of course, on the left-hand side, you always have to use the actual heating value of the fuel, right? The thing that you can get out of your fuel, right, in your burner. So we define the efficiency as QR actual over QR ideal. Let's rewrite the energy equation without the m.0. Okay. So I'm using these two. Let's just use the energy equation. So using just the energy equation, what we can do is to find the fuel to air ratio based on the output energy, input energy, and the actual heating value. Okay. So as always, let's play with this equation a little bit, ratio a little bit, and let's see what we can get out of it. You can actually divide the whole thing by H0, which is your energy at the station 0. Right? And we define this HT4, which is your burner total enthalpy, exit total enthalpy, divided by H0 as tau of lambda. This is something that you just have to memorize, I guess, because it's a little harder compared to other ratios that to conceptualize, if you will. But tau of lambda is essentially your cycle thermal limit parameter, right? Which is your exit temperature of the combustor divided by your ambient temperature. Does it make sense? Okay. And then H3 over H naught, if you multiply and divide this by HT2 divided by HT2, and just rearrange this a little bit. Let me actually write it down here. So HT3 over H naught, if you multiply it by HT2 over HT2, which is the inlet, which is your diffuser outlet or your compressor inlet, right? That's station 2. If you don't remember the stations, let me know, because we can always go back, right? This is your compressor temperature ratio, right? Your tau of C. And this is your diffuser temperature ratio, or tau of R, right? So which means that we can actually find the fuel to air pressure ratio using your efficiencies and all the other design parameters, like the temperature ratios that you have, your burner efficiency, your ideal heat value of the fuel, and the enthalpy of the ambient air, essentially.
I'm sorry, I just missed what tau R was.
Tau is HT2 over H naught. Okay? So for whatever reason, your book doesn't use tau of D here for HT2 over H naught, which is what we used before. Right? Tau of diffusion. So they're using tau of R. But I'm just following the book. Is this clear? And your TS diagram for this case, for the combustor case, we have the TS diagram that goes from station T3 to T4 here. Okay, so this is essentially a very small discussion on the combustor, but this is the only thing that we want to get out of the combustor. These are the only things that we are going to see from the combustor. You just make sure that this is, yes. Okay, eventually if you get a question, or if you were to design a jet engine, what you want to get is the fuel to air ratio, right, for a preset combustor exit temperature. But the combustor exit temperature is a design parameter, right? That's going to be your temperature limit, right? You want to always avoid that temperature. You want to design your fuel to air ratio and all of the other parameters in a way that the temperature doesn't go as high up as your limit temperature. Does that make sense? So let's do a quick summary.
Then lower temperature just so you don't burn your turbine blade.
That's the idea, yeah. Yeah. So let's do a quick summary of the combustor or burner. The fuel is characterized by its heating value, QR, which is the maximum releasable thermal energy per unit mass. The idea of the burner efficiency comes from the fact that you will never get the maximum releasable thermal energy per unit mass from your fuel, right? And it's going to always be smaller, right? The burner is characterized by its efficiency A to B and its total pressure ratio. Burning at finite Mach number, frictional losses on the walls, and turbulent mixing are identified as the sources of irreversibility. The fuel to air ratio F and the burner exit temperature are the thrust control and engine design parameters. We already know the last part. Let's solve an example. Again, this is an example from the book. A gas turbine combustor has inlet conditions of T3 total temperature at the inlet 800 Kelvin, PT3 of 2 megapascals, air mass flow rate of 50 kilograms per second, gamma 3 of 1.4, CP3 of 1.04, and we are adding a hydrocarbon fuel to it with an ideal heating value of 42,000 kilojoules per kilogram at a rate of 1 kilograms per second, which means that your m dot f is 1 kilograms per second. The burner efficiency is 0.995, and the total pressure at the combustor exit is 96% of the inlet total pressure. Which means that combustion causes a 4% loss in total pressure. Gas properties at the combustor exit are gamma 4 and CP4, and we are supposed to calculate the fuel to air ratio and the combustor exit temperature. Okay. So there is one huge difference between this problem and the previous problems that we've seen. As you can see, the inlet gamma and CP is different from the outlet gamma and CP. Why is that?
Big jumps in temperature.
What are the other reasons that may be causing this? That is the main contributing factor, yeah. So you're essentially, we usually assume that CP doesn't change with temperature, right? So we are not really concerned that much with the big jumps, because that's the first assumption is that CP doesn't change with temperature, right? But the main contributing factor here, and we are already making the assumption that CP doesn't change with temperature. The main contributing factor here is that your outlet is not air anymore, it's a mixture. Right? So its CP and other values are going to be different. We don't need to have the CP of the fuel itself because we are given the QR, and that's the only thing that we are really concerned about when dealing with fuel. Okay, so let's answer this question. Part A is asking us to find the fuel to air ratio. So how would we go about doing this calculation? Okay, what is that? Fuel to efficiencies. Fuel to air ratio. M dot F over M dot naught, right?
Yeah.
So what is 0.02, yeah. It's so easy. 0.02. Okay, the next part is the combustor exit temperature. Is asking us to find the combustor exit temperature, T4 and PT4. Okay, how can we do this? What's that? For temperature ratio, which? Oh, this one, right? Yeah. But do you have T naught?
So use the equation HT3 plus FQR HKB equals 1 plus F HT4.
So the energy equation, right? Yeah. essentially this equation, right? It's the same equation as Tala is mentioning, right? It's just a variation of that equation. But that's the only equation we have, so it's not can we use it, we have to use it, right? That's the only way. But which variation should be used, right? So essentially what Ryan is saying is that we can actually find the HT4, right? Total energy at the outlet. And how can we calculate the temperature then using H, the total energy?
H is CT times change temperature.
That's the idea, but you just have the only thing that you have to be mindful of is that here you have to use CP4 multiplied by, so HP4 is HTP4 is CP4 multiplied by T, right? That's it. So do this calculation and see what you're going to get for temperature. What about pressure? That's it. Yep. So that's 0.96. We have the pressure ratio. That's 0.96 multiplied by the 2 megapascals. So again, just to make sure that we are all on the same page, HT3 here is CP3 multiplied by TT3, right? But HT4 is CP4 multiplied by TT4. So you don't want to make that mistake. Anyone? I guess you have to do a lot of calculations to get there. Let me actually give you the final temperature and move on, because I assume you're only doing fly and chug at this point, right? So your total temperature is going to be 1390 Kelvin, 90 Kelvin. Okay, and your total pressure is going to be 1.92 megapascals.
What did you say the temperature was?
1390.
And pressure
1.96, no, 92, 1.92. Okay, so moving on to turbine. So turbine, what you see here is essentially a combination of a compressor, which is a compressor and a turbine, which are connected to each other through a shaft, right? And in our cycle, in our kind of cycle, we have the compressor, and then we have after the compressor, we have the burner, and the turbine afterwards. But the power of the compressor is generated by the turbine and is is moved to turbine from through the shaft, right? But what is the job of a turbine? Job of a turbine is the flow expansion. What is flow expansion? Flow expansion is the flow process, essentially in a turbine, which involves significant static pressure drop with a static temperature drop. So essentially, at the exit of a turbine, you would expect to see a lower pressure, colder gas. That's the idea, right? And your HS, let me ask you this before talking about it. So for the burner part, we represented a TS diagram instead of an HS diagram. Why was that? It goes back to the fact that the CP at the inlet station and the outlet station of burner is going to be differently, right? So a TS diagram is definitely different from an HS diagram, and it is harder to examine because there we are going to have two factors in the changes in enthalpy. One is going to be CP, one is going to be temperature. So you want to just isolate the variation to only temperature. That's why we use TS in a burner. But in all other parts of the jet engine, we can use T or H, doesn't really matter because the only variable is going to be temperature, right? Your total input. But so this is what the process of a turbine looks like. We go from station 4 to station 5. We are going to lose a lot of total enthalpy essentially, and the entropy of the system will increase. The ideal case of a turbine process will be an isentropic process when you lose your total enthalpy to an isentropic process and you don't have any increases in entropy. So based on this HS diagram, based on this HS diagram, how would you characterize the efficiency? How would you formulate the efficiency of a turbine? Your ideal power is always higher than your actual power. Actual or ideal. So essentially, in a turbine, you want to be able to lose as much energy to the shaft as possible, right? You want to make it as big. You want to lose all of the energy. You want to actually absorb all of it, or you want to transport all of the energy from the air to the shaft, right? Or to the whatever you want to transfer the energy to in a turbine. Okay, does it make sense? Yes? That's why we will have the actual power to the ideal power, but we'll talk about it later. So let's write the conservation equation. Conservation of mass. Your M of turbine is essentially inlet and outlet are essentially the same. Your mixture is going to be your mixture mass flow rate, m dot naught plus m dot f, or 1 plus f m dot naught. Your energy is being transferred from air to the shaft or wherever you need the power. Okay? Energy is being transferred from air to your shaft, let's say shaft. So your total power output of a turbine can be calculated by the amount of energy change, the total enthalpy change between the station 4 and station 5. You want to get a positive value for it, of course, so you use the higher value, which is HT4 first minus HT5, right? So that's why we do inlet minus output. And that will give you the actual, the HT4 minus HT5 will give you the actual energy change, if you will. And we said the ideal case in a turbine is the isentropic process, which we go from HT4 to HT5S isentropically. So that will be your ideal case. Based on this, we can find the turbine efficiency, which is going to be your delta TH actual over delta HT, H of T isentropically. Okay, can we replace it with temperatures here? Sure, why not, yeah? So let's have a look at the temperatures and their relationship to the total pressures. For the denominator, we are talking about the isentropic relationship, so we can find that we can use the isentropic relationship between the temperatures and pressure to replace pressure here, the pressure ratios here, which essentially means that your T5S, T5S represents the station, exit station of the turbine when you get there isentropically, right? Divided by TT4, which is the inlet station of the turbine, is going to be equal to PT5S over PTT4 to the power of gamma minus 1 over gamma. So it's going to be equal to the pressure ratio. And we can replace this here. We can replace what we have done here versus the other efficiency equation is that we have divided everything by HT4, right? And the HT4s will cancel. We essentially, if you divide everything by HT4, you're going to get 1 minus TT5 over TT4 over 1 minus T5S over TT4. Here, the same as the compressor stage, we can define a small stage efficiency E of T as this. E of T is going to be your actual elemental change or small changes in enthalpy versus the isentropic small changes or elemental changes in enthalpy, right? And we can actually have the exact same, not the exact same, the similar relationship between the temperature ratio and the pressure ratio, the real pressure ratio, similar to the compressor we had, right? If you recall, the temperature and pressure ratio of the compressor, the relationship was similar to the isentropic relationship. You just had to add a small state efficiency in the denominator over there, in the denominator of the power, right? You remember that? So essentially, it's going to be pretty similar to what we have for the compressor. Just the place of the small state efficiency is going to go to the numerator. Tau of T is going to be equal to pi of T to the power gamma minus 1 multiplied by E of T over gamma. We of course find the pressure. We can find the pressure ratio using the temperature ratio with the exact same equation as well. Just that power has to be transferred to the other side. And using this, so we have the pressure with temperature ratios here. Using this relationship, the regular isentropic relationship, and the actual relationship, we can rewrite the efficiency of the turbine as H of T equal to 1 minus tau of T, which is the temperature ratio, right? TT5 over TT4 over 1 minus tau of T to the power 1 over E of T. Is there any questions? No? Okay. So let's move on. can actually find the turbine expansion ratio is 1 over tau of T as a function of turbine of adiabatic efficiency. For different small stage efficiencies, here we have only represented one small stage efficiency of 0.9. You can see for higher expansion ratios, which means that for lower temperature ratios, essentially, we are going to get a higher efficiency. But the other important part of the turbine is the energy balance between the turbine and the compressor. The idea is that the shaft power of the turbine goes to the compressor, right? So whatever power you have in the turbine must be equal to whatever power you have in the turbine. How did we calculate the power generated in the turbine? M dot, this is M dot multiplied, M dot O multiplied by 1 plus F multiplied by the changes in total enthalpy. For a compressor, our M dot is only M dot naught, and just have to multiply it by the total enthalpy change of the compressor, which is HT3 minus HT2, right? If you play with this a little bit, if you just like take the HT4 out here, for example, and divide it by an H, divide the whole thing by an H. Now you have to play with it to get from this equation to this, but you will definitely get there if you play with it. You can actually find this as a function of temperature ratios or taus, right? What was tau of lambda? Does anyone remember? HT4 over H naught, exactly, right? Multiplied by 1 minus tau of T, which is equal to be tau of R, multiplied by tau of C minus 1. And we have and all of these are temperature ratios, except for tau of lambda, which is an enthalpy ratio, right? Any questions? So we can find it based on this. We can find the temperature ratio of the turbine as a function of a compressor temperature ratio, the tau of R, tau of lambda, and fuel to air ratio. But what will happen if not all of the energy generated in the turbine gets to the compressor? And that's always the case, right? Because you will have a lot of losses that is going to happen. And the shaft that is going to transport the energy from turbine to the compressor will have a lot of bearings, will have a lot of things that will require energy themselves, right? So essentially, we always have the total energy in a turbine always is equal to the total energy of the compressor plus the energy change in the bearings, right? We call them the mechanical energy needed to transport the energy from turbine to the compressor. But some of the energy that is generated by the turbine is actually sent to an electric generator, some of the shaft energy is sent to an electric generator to be used in the aircraft, right? That's very important. So that's some of the loss we're going to have as far as the energy transported from turbine to compressor goes. And we actually, in our analysis, if you're only concerned about the cycle of the jet engine, we don't really care about the bearings and the electrical generator or whatever, right? We all combine all of those things together in a term called the mechanical efficiency of the system. That mechanical efficiency, which is going to be eta m, is you have to multiply it by the total energy generated in a turbine to get the energy generated in a compressor. Any questions so far? And we just have turbines adiabatic. I just talked about it. So the other part of the turbines that we need to focus on a little bit before going to solving an example is a multi-stage turbine. So as the same as compressor, we can have multi-stage turbines, and we also have something in turbine which is called the turbine cooling, right? And it's going to happen at different stages. So essentially what happens is you get the cold air from the compressor, different stages of the compressor, to cool down the air at different stages of turbine, right? Just the only part that you have to be mindful of is that you have to make sure that you get the air from the correct stage of the compressor. What does it mean? It essentially means that you have to make sure that you're getting the air from that stage of the compressor that has the equivalent pressure at the turbine stage, right? Or higher pressure, right? Because you don't want to get flow going back into the pump, right? You always want your compressor flow to be mixed with the turbine flow and make it a little colder. That's the idea. But the turbine cooling, all of these stages and everything, we'll talk about later. And yeah. Any questions so far? Okay. So let me actually ask this question, which is a little off topic, but seeing this picture reminds me of that. I'm pretty sure you guys have heard this the terminology used for the jet engine. They call it the power plant of the aircraft, right? Why do we call it the power plant of the aircraft? But the power plant means a specific thing, right? The power plant is a place where you like burn fuel to generate electricity and give it to a city, right? In our terminology, in a mechanical engineer terminology. What is essentially what I'm asking is what is similar between a jet engine and a power plant that generates electricity for a city? Can you say it louder? So it's yeah, exactly. So essentially, you essentially have a cycle, right? It's a closed cycle over there. It's a little bit, usually a closed cycle, not always. But you're going to use the exact same phenomena. So my point is, if you understand how to do the calculations of the pressure ratios and efficiencies and everything, and if you understand these different stages of the compressor and the turbine, you will be able to design a power plant as well. It's the exact same mechanisms, exact same analysis, exact same cycle analysis. The only difference is going to be the sizes and the pressure outputs and everything, right? So if you understand this, you essentially are understanding the cycle, thermodynamic cycle analysis in general, and you will be able to design any device that uses a cycle. Does it make sense? Okay. Yeah, I just wanted to make sure. I should have mentioned it much earlier, but just remember I have not had. So for the HS diagram for a multi-stage turbine is going to be a little different. It's not going to be a straight line, of course. It's going to have all of these zigzags in it. And we'll get to this a little later, but let's do a small mathematical analysis on whatever that is happening here. So let's forget about the first equation because I think we don't have the time for it. But let's get to here. Let's say you are, and what you want to do here is essentially analyze the cooling system that's cooling from the compressor that's coming in from the compressor to a different stage, to a specific stage of a turbine. Okay. Let's look at that specific stage where the cooling is coming in, right? We want to write an energy balance. Does that make sense? M.C, how can we write the energy balance? The energy balance is essentially going to be whatever the energy of the coolant coming in is, plus whatever the energy of the hot gas that is inside the turbine is, those two must be equal to the total energy of the mixed fluid. Does it make sense? So energy coming in, the coolant energy coming in, m dot c, plus the energy of it is HT and C. So this C stands for the cold air coming in. For whatever reason, your book uses G for hot gas. I assume H would have been a little more appropriate here, but m dot G multiplied by HT of G is the energy of the gas inside the turbine, right? That's already hot. And a combination of those two, essentially the energy of the mixed gas is going to be the mixed gas mass flow rate, which is m dot C plus m dot G, right? Multiplied by the enthalpy of the new gas. Does it make sense? Yes? Pretty simple. This ratio of the energy is something that is usually is talked about a lot, right? The ratio of the enthalpy of the mixed gas and enthalpy of the hot gas coming in. So using this definition that we have had here, we can actually find an equation for this specific ratio. We can use the conservation of energy equation that we just had earlier to find the numerator of this equation, and then we can do the same thing for the denominator. Which if you play with it mathematically a little bit, you will get to this relationship. So the ratio of the mixed gas enthalpy to the hot gas enthalpy is going to be equal to 1 minus m dot C, which is your m dot of the cold gas over m dot G, okay, multiplied by 1 plus m dot C HTC over m dot G HTG, okay? Does it make sense? This is actually I think the one question in your homework relates to this, which is simply calculating. As far as I remember, just has to be calculating the HT of the mixed gas, but you have all other parameters. So just plug and chug, right? Yeah. I just want to make sure that you guys remember, you guys know how we got from here to here. So I just written the mathematical relationship we have used. So this is 1 over 1 plus this, right? Which is a very small value. M dot C is much smaller than M dot G, always, right? So we can use this mathematical relationship to transform this 1 plus m dot C over m dot G, bring it to the numerator essentially, and make it 1 minus m dot C over m dot G. Right? This is a mathematical relationship. And multiply to whatever we have over there. Is there any questions so far? So we are already done. I guess, but the next class is a little aggressive with timing. We are gonna stop here. They always keep coming in, right? So we are going to stop here. For the next lecture, we are going to solve a nozzle example. And we are going to solve a turbine example. We will talk about nozzles, and we will finish the turbo jet engine cycle analysis, essentially. Right? And then we will start working on the turbofans and the afterburners and so on and so forth.